Okay, good morning. All right, I pulled up the course calendar here. I guess what? Exam is tomorrow night. I hope that's not a shocker to anybody. So today we're going to do some review in class. Tomorrow when you go to recitation, your TA will do more review. And of course, I have office hours today, and your TA might have office hour today or tomorrow. Take advantage of those if you have questions. Also look ahead to Friday, September 18th. No class on Friday. Because of the evening exam, we have to give you a day off. So that's this Friday. Again, you shouldn't be cheering for missing wonderful class. All right. Location. Okay. Again, it's based on who your TA is. Make sure you go to the right place and show up at the right time. All right? So this thing is on the course web page. Take a look at it, scroll it down, and make sure you know roughly where you should be in the room. If you show up, you don't know where to go, just find your TA, and he or she will point you to the right place. All right? By the way, there's a typo here. Should be physics. So if you're in Nick Winovich's class, you go to Physics 112. There's no such building on Purdue campus as PHS. So that should be physics. Okay. There's also SI session tonight and tomorrow. If you want some last-minute question answering, feel free to go to SI. They will not do the studying for you. You should show up having already studied, but have questions that you want answered. Okay? And Jimmy Dixon is canceling his session tomorrow evening because it's right after our exam. We figure you probably won't have any question for him. So we decided to give him a day off. He deserves it. Okay, so I'm going to go through a few major topics that you have to know for the exam tomorrow night. And by the way, if you have not been goofing off, if you've been doing your homework, going to class, you'll be okay. It's not a terribly difficult exam. We have exam 2 and exam 3 for that. No, I'm kidding. It's a very reasonable exam. Like you said, if you have been doing what a student should be doing, you will do fine. Okay, I'm not going to say too much about the 3D coordinate system. I think most people have no major problems with that topic there. Be sure you can recognize the shape of a graph. For example, if in 3D we give you an equation x is equal to 3, you need to be able to tell us what shape it is. Things like finding the sphere's center, radius kind of thing. Okay, so like I said, I'm not going to say too much about that topic. Let's talk about vectors next. Let's say I got two vectors, 1, 2, 3, and minus 1, 0, 5. Things like a plus b and a minus b, that's pretty trivial. I'm sure everyone can do that. Things like 3a minus b, for example. So these are pretty trivial things. I'm not going to talk about them. You should be able to do. Let's focus on the two products that we have looked at. And also, you need to know, for example, the magnitude of A, that kind of thing. So dot product, when you take the dot product of two vectors, you multiply the components together, just line them up, and then add them up together. Right? And here we get 14. So that's easy. And one major reason we use dot product is to find the angle between two vectors. Okay, so who remembers the formula for the one with the angle? Good. Very good. Right? So that's a formula that gives us the angle between two vectors. Let's take a look at what we got here using these two vectors. A dot B we calculated earlier is 14. And what about the magnitude of A? What do we get? Root 14. Is that right? Yep. Good. How about B? Radical 26. Excellent. So this tells us that the angle between them can be found by taking the inverse cosine of that. Okay, and we're not going to give you this number on the exam to calculate. We'll give you something that you can recognize. So the special angles, right? You should be able, the numbers we give you on the exam will work out, and you'll end up getting a special angle that you have to be able to recognize. Okay, so that's the dot product. Then we had cross product. Right, so using the same two vectors, we got 1, 2, 3, and minus 1, 0, 5. Let's find out the cross product. So we went over the way to calculate the cross product using the determinant, right? Now be very careful that the order is important. So the first vector must show up in row 2, and then the second vector must show up in row 3. Because we all know that A cross B and B cross A are not the same thing. So be careful that the order has to be correct. Okay, remember how to calculate this stuff? Yeah. For the first one, you cover the first column and then the first row and take the determinant of that. So we get 2, 3, 0, 5, and this provides me the I component. What's the special thing about the J component that we have to remember? Very good. We have to change the sign. We cross out the second column and then the top row. And then the last one, same idea. That gives us the K component. Right? For 2 by 2, we multiply the diagonal together, subtracting away what we get when we multiply the off diagonals together. So here we get 10 minus 0. 10i minus 5 minus minus 3, so that's 8. Here we get 0 minus minus 2, so positive 2 for the k component. Right? What's the geometric significance of the vector we got out by doing A cross B? Absolutely, excellent. So just like he said, what we get out of this would be perpendicular to A and B, right? And how do we determine the direction? The right-hand rule, excellent. The right-hand rule for the direction. So for example, if my A is pointing like this, my B is pointing like that, where is A cross B pointing? Good. Right? A cross B, so it comes out of the page. Out. Oh. If we want to find the area of a parallelogram formed by these two vectors, how can we do that? You said something? Dot product or cross product? Yes. Who said yes? What do you think? Cross, dot, cross, yes. Just a cross? Good, excellent. Yep, we take the magnitude. If you just take a cross, you get a vector, right? It makes no sense to say the area of something is a vector. The area is a scalar quantity. So we take the cross product, we take the magnitude. What might happen is we could give you, let's say, 4 points. In that case, what you need to do is just to find two vectors among those 4 points. And then that would give you the two vectors A and B that you need. Okay? Sometimes you'll get an angle between the two. So there's another way to calculate the magnitude of A cross B. Who remembers that? Right, it looks awfully like the dot product formula. Oops, sine theta. That's horrible. Let's do it again. There we go. Okay? All right, so that's the cross product. Make sure you know which one gives you what. The dot product gives you a scalar, whereas the cross product gives you a vector. Projection. We need to know how to find a projection. of a vector onto another vector. So this red vector is a vector projection of B onto A. Remember, we write it that way, PROJ, the vector that's on top, projected onto the vector that's used as the subscript. So this is a vector projection. The length of the vector projection is the scalar projection. All right, and we write it COMP for component. Make sure you know which is which. And to find a projection, we use the dot product. So keep in mind that a projection is always related to a dot product. So this gives us the length, and this is a scalar, right? And as long as you remember this formula, the other one is very easy to remember. The other one is a vector that is this long and pointing in the A direction. In other words, it's a vector with this magnitude and goes in the same direction as a unit vector pointing in the A direction. This gives us the magnitude, and this is a direction. And to specify directions, we have to specify by a unit vector so that we don't change the desired magnitude. All right, so make sure you know the two projections, which is which, and how to calculate them. And then we move into the integration part of the stuff we covered. We started with the area between curves. So let's do this by example. We're looking for the area bounded by x squared and 1 minus x squared. Let's get two reasonable sketch. Let's make this a 2. Let's get two reasonable sketches here. X squared, we all know, is just a parabola opening upward with the vertex at 0. The other one is the same thing, pointing down, opening down, and the vertex is shifted up to y is equal to 2. So something like that. Okay, so how do we do this? Find the intersection. Good. And how is that done? Very good. Now you see why I made it a 2. All right, so we found the intersections at -1 and 1. Then what? Okay. We take the top minus the bottom. And what else do we do to that? Good. Integrate from the left to the right, right? So we start at the left boundary, -1, end at the top, at the right, which is the right boundary. Top minus the bottom, so 2 minus x squared, that's the top, minus another x squared, dx. Okay, on the exam, as long as you can set things up, you end up with an integral that's pretty easy to calculate. Maybe not as easy as that, but something pretty reasonable. So the integration part won't be too difficult. And I'm going to leave that just like that, and you can calculate the integral. You also need to know how to integrate when the curves are left and right. So if I just switch x and y, then I'll end up getting exactly the same shape, but my parabolas will be opening to the right and to the left. X is equal to y squared. If you see y being squared, that tells you there's an x-axis symmetry, up and down symmetry. Y squared is always positive. That means x is always positive. Therefore, it has to open to the right. If it opens to the left, then x is always negative, but something squared is always positive. So it has to be like that. The other one with a minus sign in front is opening to the left. And when that's 0, x is equal to 2. So there we go. You get this kind of shape. Same process, right? We still have to find the intersection. We integrate the stuff. Exactly the same shape. So very quickly we could find out that if they would intersect at -1 and 1. And this time we integrate what? Not top minus bottom anymore. Right. The right minus the left. Right is the more positive x. Left is the less positive x. Top in the previous one had a more positive y, right? And the bottom had a less positive y. So everything is the same. We're just changing the rows of x and y. And we would integrate from the bottom to the top of the region in terms of y. Okay, and then we extend that to find, we use that to find volumes. We cover two methods. The disk/washer method, and the other one is the shell method. Let's again do this by example. Let's rotate the region bounded by x squared and y cubed, no, x squared and x cubed, about the x-axis. Okay, so x squared we already saw in the last problem. What does x cubed look like? Yeah, it looks kind of like this, except this one here is reflected down to the below the x-axis. Now the question is it above or below this? It kind of depends what x it is, right? What if we choose a very small value of x, let's say 1/2? If you choose a small value of x, you can find out whether this is above or below that. 1/2 cubed is obviously smaller than 1/2 squared. So that's telling us that the x cubed is below. If x is small. Where do they intersect? This we can actually do by inspection. 0 and 1, yeah. Right? 1 cubed and 1 squared is the same thing, so it's 0. And that's the only place they will intersect. So therefore, let me blow up the relevant region here. We're taking this to go about the x-axis. Do this carefully. Let's set up the rectangle. Now, which way do I set it up? Do I want it perpendicular or parallel to the axis of revolution? Perpendicular. Good. The disk/washer method is always perpendicular to the axis of revolution. So here's my axis. Therefore, I want to set it up like that. And that, when you revolve it, gives you that washer. So we set up the volume of one washer and then let integration take the rest. So in this case, we will use we need to do the outer radius, the disk from the outer radius, subtracting away the disk from the inner radius. That gives us the hollow washer times the thickness. and the outer is x squared, right? And then the inner one is x cubed. And then we let the integration accumulate all of these washers for us. We integrate from the left to the right, 0 to 1, pi times x to the 4th minus pi x to the 6th. And once again, the integration we'll ask you to do will not be difficult. Will be pretty reasonable, as long as you set things up correctly. Yep. All right. And in practice, you can take the pi out and integrate term by term pretty easily. So that's the disk or the washer method. Questions? Okay, good. Let's do the same thing with shell. We're still going to go about the x-axis. All right, exactly the same set of curves, so the last sketch is still relevant. And this time, the rectangle must be parallel. Parallel to the axis of revolution. Since we're setting up the rectangular horizontally, the thickness will be dy. And that's a clue to you that these equations need to be switched around to x in terms of y. So how do you calculate the volume of one shell? What's the general formula we use? Right, 2 pi, radius, good, times the height, right, and then the thickness. I'll put a height in quotes because in this case it's kind of lying on its side. All right, so we get 2 pi, and what would the radius be? And how do you measure that? When this thing is revolved around, get this cylinder here. And notice that the x-axis comes out like that. And if you look at this cylinder from this way, you'll see the radius. And the radius comes from revolving that rectangle, right? So we need to measure how far the rectangle is from the axis of revolution. So this distance right here would be our radius. And in this case, it would be, right, y. The distance from y equal to 0 to any arbitrary y. So that's y. Height, that's pretty easy. It's the right minus the left. Thickness is dy. And now the entire thing, we let integration do the rest for us. Zero to, where would this be? One, right? They also cross each other at 1 in both directions. In practice, let's multiply this in here before we do the integration. And you take the 2 pi out, integrate term by term, evaluate 0 to 1, and that will give you the same volume as the last one. Should be exactly the same. It's the same shape, exactly the same volume. Okay? Now, on some problems, we'll give you the curves and tell you which axis to rotate about. So on those problems, you can use whatever method you want to calculate the volume. But on certain problems, we will test you on a specific method. And just read the problem carefully and then set it up. On problems like that, the answer would not be, we wouldn't make you choose numbers from the list of answers. We'll make you choose from a bunch of integrals that you should get if you use the specific method that we specified. So in other words, you need to know how to do both. You cannot get away with just one. You also need to know how to find the volume of an object if we give you the cross-section. Here we have a pyramid. It's got a square base with each side being 1, whatever unit, and a height of 3. So here's my pyramid. Okay, it's got a square base. It's 1 all the way around. And it's got a height of 3. So this is not a revolution problem. There shouldn't be any pi in your answer. The pi comes out because we're revolving around some kind of circular end result. Here, there's no such thing. There's no pi in the answer here. But the way we do this is exactly the same. I take a slice of that. Find the volume of that, and then integrate from the top to the bottom or bottom to the top, whichever way, let the integration do the rest. So this is the tricky part here, to calculate the volume of the slice. Notice that this square, the side of the square changes with the height. We have to find a relationship to find the volume correctly. Let's take a look at this pyramid from this point of view, looking that way. So if I do that, I see a triangle. It's got a base of 1, so I'll split it 1/2 here and 1/2 here with a height of 3. So this is what I need to know, right? If I can find out that, then I can calculate the volume. And we need to express that as a function of y. And let me call that D. And the easiest way to do that, we've seen this many times, is to use similar triangles. The big triangle has a base of 1/2 and a height of 3. And then the small triangle has a base of D and a height of 3 minus y. So from there, we see that this short side D here, depending on y, is 1/6 times 3 minus y. Then you calculate a slice. It's a square. Each side is 2D, right? D is half of it, times the thickness. So that's 4 times this thing squared. Then you're integrating y from 0 to 3 to find the volume of that pyramid. Okay? Okay, running out of time here, so let me just mention the things you have to know for the exam. Make sure you know how to find the work that a spring does, being stretching it, being stretched. Make sure you know how to find the work when you pump a tank empty or half empty. and also the average of a function. That one's pretty easy. You just have a formula to apply. And look over the homework you did with these things here. As long as you know how to do the stuff you did on homework, you'll be fine for the exam. We're not going to give you tricky units. Just trust us. When we give you a unit, everything works out for the problem. Okay, that's it. I'll see you tomorrow night.